Hi everybody, Augie Kennedy here again with Super Awesome Calculus. And today we're going to be taking the test on Chapter 5 entitled the Fundamental Theorem. Alright, so last time we talked a little bit about the substitution rule and explained its relationship to the chain rule for differentiation. So I left you a problem and we're going to go over that problem right now. Now, what I asked you to do is I asked you to use the substitution rule to integrate the following function. The integral of x times the quantity x squared minus 1 cubed dx. So let's write this on the board. You've got your integral x times the quantity x squared minus 1 cubed dx. I'm going to turn I'll turn the light on. Here we go. Okay, that should help. Now, looking at this, your first goal is to identify whether or not it's a simple integral that we already know how to integrate. Unfortunately, you have a product here, x times x squared minus 1, so it's not going to be a simple integral, and therefore you'll want to try to find a suitable substitution. Now, I mentioned some strategies for finding substitutions, and one thing to do whenever you have parentheses or radicals is look at the function inside that radical, differentiate it, and see if you can find a part of it in the entire integral. So we look at the parentheses, which is x squared minus 1. Well, if we differentiate that, we see that we're going to get 2x. And we already have an x outside, so it looks like x squared minus 1 might be a good choice for substitution. So let's go ahead and do that. Let's choose u to be x squared minus 1. Now remember, we need to find out what du is, because the substitution rule is for f of u du, not f of u dx. So, we've got du, we just differentiate u with respect to u, and we get 2x dx. Now we're dealing with something, because now we can get x dx by itself by dividing du by 2, and then we have du over 2 equals x dx. Well, this is great, because we have x, we have dx, and we've got u cubed. So the new integral is very simply 1/2 times, we got u cubed du. Now we know how to integrate that function. It's very simple. We just take use the power rule for integration, which would make it u to the 4th over 4 times 1/2, or u to the 4th over 8. But we also remember that we can't leave the answer in terms of u. So we just find out what u is. We know that u equals x squared plus 1. That was the substitution we made. So we plug in x squared minus 1 in place of u. And we get x squared minus 1 to the 4th power over 8, and never forget plus c. Because remember, whenever you're using an integral, you need to include the plus c at the end to take into account any constant variability. Alright, so that was the big problem that I gave you guys. Now today, we have a test. Now this test will be pretty simple. It's mostly going to test your knowledge on the understanding of integrals, and namely the fundamental theorem of calculus. I'm not testing you on substitution, because we just did a substitution question. So anyway, go ahead, take the test. You've got 5 questions, and at the end of the 5 questions, I'll just, after showing the 5 questions, you can pause the video during the question or write it down and work it out. And after all 5, I'll be back to explain how to do each one of them. Alright, good luck. Alright, welcome back. I hope you had a good time taking the test, and let's jump right in and start solving it. So the first thing I asked you is I asked you to explain exactly what is meant by the statement that differentiation and integration are inverse processes. Now, you could have had a wide variety of answers here, but what I'm basically looking for is some kind of variation on the fundamental theorem of calculus. Whether or not you stated this as a sentence, or whether you wrote the explicit formula, it should, one of those two things should be in your answer. So for instance, we know from part 1 of the fundamental theorem of calculus that the derivative of the integral from a to x f of t dt equals f of x. In other words, the derivative of the integral gives us the function evaluated at the upper limit, f of x, which is very, very useful because it says that if you've given f of t dt and you want to get to f of x, you can take the derivative of the integral. So by using those two cancellation operations, you get back at basically the original function. So that's one way to look at them as being inverse processes. Another one is to look at the second part of the fundamental theorem of calculus, which is the integral from a to b f prime x dx, big F prime x dx, is f of b minus f of a. Now you might be looking at this and wondering, well, why is it big F prime x dx? Well, just remember, if it's little f, if it's just f of x dx, that's the way that we normally write the fundamental theorem of calculus. But remember that the goal there is to take an antiderivative. And an antiderivative's derivative is the original function. So, sure enough, by writing big F prime, the antiderivative, and taking the derivative of that, we have regular f of x. We have the original function. So that's another way of looking at how differentiation and integration are inverse processes. All right. Now the second question I asked you was a true or false question. I asked you, true or false, if f is continuous on the closed interval a to b, then the integral from a to b at 5 f of x dx equals 5 times the integral a to b f of x dx. So let's write this out. F is continuous on ab. Now I asked you if this integral from a to b, 5 times the function f of x dx, was equal to 5 times the integral a to b f of x dx. Now, if you remember the rules of constants multiplying by derivatives, constants times limits, and therefore constants times integrals, you'd realize very quickly that this answer is true. It's true. Where it's not true, and one thing that I want to just alert you to with this question, a constant, the integral of a constant times a function is that constant times the integral of a function. But if you have something like this, a to b x f of x dx, that does not equal x times the integral a to b f of x dx. In fact, that x f of x dx indicates that we might want to look to see if we can use substitution, or as you'll learn later, the concept of integration by parts. Well, you'll learn that in Calc 2. All right. Now we get into the exercises. These exercises, I hope you found them to be fairly easy. I think they're a nice respite from the fairly hard exercises that you had last test. So the first exercise I gave you was to simply evaluate this integral. This integral was from 1 to 2 of 8x cubed plus 3x squared as a quantity dx. This is very easy. It's a very basic integral where we're going to be using the power rule. So we have this integral from 1 to 2, 8x to the 4th over 4. Remember, it's x to the n plus 1 over n plus 1, with n being 3. So 8x to the 4th over 4. Plus 3x to the n plus 1 over 1. N is 2, so n plus 1 would be x cubed over 3. Evaluated between 2 and 1. Well, we can also simplify this to say that this is really just 2x to the 4th plus x cubed between 2 and 1. You'll see how the 3's cancel, and 8 over 4 becomes 2, so we get 2x to the 4th plus x cubed between 2 and 1. So let's go ahead and let's use the second fundamental theorem of calculus, or the second part, and let's plug in the 2 and then subtract the 1. So that would be 2 times 2 to the 4th plus 2 cubed, that quantity, minus 2 times 1 to the 4th plus 1 cubed, and we would get 32 plus 8 is 40, minus 2 plus 1 is 3. So the value of this integral, the value of the integral between 1 and 2 of x cubed plus 3x squared dx is 37. All right, 40 minus 3. So that one wasn't too bad. And I hope that you don't think this next one is too bad either. Although I did ask you a question here that requires the first part of the fundamental theorem of calculus, which a lot of teachers tend to gloss over for some reason. Well, here we go. I gave you big F of x. It's from, I don't know what number that was, but let's just say it's a to x t squared over 1 plus t cubed dt. And I asked you, all right, well then what is big F prime x? Well, this is a very direct application of the first part of the fundamental theorem of calculus. You might remember that that one time we had from a to x to the 4th as an example, and we had to let u equal x to the 4th and do a substitution. You don't need to do that here because we only care about the upper bound, and it's x. So direct substitution of x into, oh no, my phone. How embarrassing. Wow. Anyway, so a direct substitution of x into this function will give us what we're looking for. So, we got x squared instead of t squared over 1 plus x cubed. Now what does that mean? That means that the derivative of the antiderivative is this x squared over 1 plus x cubed, which is also regular f of x. So a very simple application of the first part of the fundamental theorem of calculus. And the last thing, the last question on the test, was actually even easier. It was just a practical application of what exactly an integral is. I asked you to let the function r of t be the rate at which the world's oil is consumed, where t is measured in years starting at t equals 0 on January 1st, 2000, and r of t is measured in barrels per year. Well, then I asked, what does the integral from 0 to 8 r of t dt represent? Well, the first thing you'll want to do is you'll want to write down all of the knowledge you've got. All right, we have r of t. And r of t is barrels per year. So barrels over year. Okay? T equals 0. And is that t equals 0 at January 1st, 2000. Okay? We also know that we're looking for the integral between 0 and 8. There we go. R of t dt. So all I want you to do is just find out what this means. Well, we know that we're looking at the area under the curve, because that's what an integral is, the area under the curve of r of t. And we know that r of t is measured in barrels per year, because t equals 0 indicates a year, t equals 8 would indicate 8 years later. So the metric we have is barrels per year times years. The years cancel, so we're measuring, technically speaking here, we're looking at an amount of barrels. We're mapping out the points of how many barrels per year, checking the area under that curve, and that's going to give us the amount of barrels of oil we actually manufactured, or in this case, consumed. So, what else do we need to know about it? Well, we want to know what exactly this is, because we know that how many barrels we've consumed, but we don't really know the time difference. Well, if t equals 0 was on January 1st, 2000, and we're going in years, and the upper bound is 8, that's going to be 8 years later. So, from 1/1/2000 to 1/1/2008. And that gives us our final answer. Barrels of oil consumed from January 1st, 2000 to January 1st, 2008. That's what that integral is really telling us. So I hope you had some good success there. We only have one more chapter left of calculus. I know, I'm kind of sad about that. And it's going to be all about some applications of differentiation or of integration towards volumes. And I think we'll go over the average value of a function in the next chapter, but mostly it's going to be about using integration instead of just figuring out areas, figuring out volumes of spheres and strange shapes and things like that. So that's what's coming up next, and thank you very much for joining, and take care.